ladies and gentlemen. A very good morning and welcome to all. Thank you for taking time out of your busy schedule to join us this morning. This webinar is presented to you by the Singapore Contractors Association and features two of our esteemed members. We are very happy to collaborate with Penta-Ocean for the session to shine the spotlight on digital innovations in construction and project management. According to the McKinsey Global Institute Industry Digitalization Index, the construction industry is among the least digitalized as compared to the other sectors. Generations of refinement of construction processes brought the industry to its heights of today, and it is not easy to leave such hard-earned knowledge behind in favor of newer ideas and innovations. However, recent advancement in technology coupled with changes brought about by the COVID-19 pandemic, the construction industry, along with the rest of the economy, has been motivated to digitize and upgrade together with the rapidly changing times. It has accelerated our impetus to seek out alternatives to build better and more efficiently across all areas of construction work. The construction industry is reshaping itself. Projects are ever more complex and larger in scale. The growing demand for environmentally sensitive construction means traditional practices must change, and the shortage of skilled labor and supervisory staff will only get worse. These are issues that require new ways of thinking and working. The construction sector will need to adopt new paradigms in the face of these challenges. It has become clear that we will need expediency and efficiency in dealing with the rapidly changing landscape. Digitalization can improve sustainability performance and help develop new processes, services, and market. But despite the promising benefits, the sector has been slow to fully adopt emerging digital technologies. However, an increase in productivity will be the main objective of digitalization. The benefits of such digitalization efforts may not be apparent to many due to the amount of capital investment required and the difficulty in quantifying the savings achieved at earlier stages. Furthermore, digitalization of any process requires upgrading of workers' skill and learning new knowledge, which can potentially pose a challenge for experienced workers who have well-entrenched mode of operation. However, over time, it has also proved to be a contributor in terms of enhancing productivity in the construction sector, as experienced by many construction companies in Singapore. This is especially so when there is an increasing requirement to perform more complex processes. One example is the increasing common use of the Building Information Modeling BIM system, where the design, management, and execution of building projects is streamlined and coordinated, resulting in the final product of noticeable increases in productivity. Today, employment of such digitally advanced technologies like virtual reality, augmented reality, drone use, and many other technologies are starting to gain traction. Overall, this is expected to trigger significant improvement potential pertaining to direct costs, quality, security, delays, images along the full construction value chain. Some companies may be in the slow lane while others are speeding ahead. But what is becoming clearer all the time is that the construction industry now has a roadmap towards digital transformation, and the journey is underway. This morning, we are proud to invite two speakers from our member companies to share with us their company's in-house digitalization initiatives in their projects. I would like to thank our speakers for taking time to share their state-of-the-art innovations and the thought processes and challenges behind conceptualizing and implementing these ideas. First, we will hear from Ms. Michelle Lee and Mr. Edward Armstrong from Penta-Ocean Construction on their use of civil information modeling and upcoming construction technologies to enable their company to be a technologically advanced contractor. This will be followed by Mr. O'Connell from Gammon Private Limited, who will speak on the company's IDD practices in their Sentosa Sensory Scape project. Ladies and gentlemen, I hope you will have a fruitful session ahead. I will now hand the time over to the MC. Thank you and have a good day.
Thank you, Louise. And next, our speakers are going to present to us the topic, Civil Information Modeling and Upcoming Construction Technologies. May we invite Ms. Michelle Lee, Digital Delivery Manager, and Mr. Edward Armstrong, Senior Geologist from Penta-Ocean Construction Company Limited. Over to you, Michelle and Edward.
Hello, thank you. And good morning, everyone. Thank you for taking the time out to attend this webinar, and also thank you to SCAL for inviting us to speak at this webinar. So going with the theme of this conference, that is the digitalization for a smart and sustainable built environment, my colleague Edward and I will be sharing about some of the digital technologies that we have deployed in Penta-Ocean, in Japan, as well as in Singapore, in the civil construction space. So just a short background on Penta-Ocean construction. We have several branches internationally, and our international HQ is stationed right here in Singapore. So apart from the building construction works that most people are familiar with, we also do a lot of marine and port construction works, as well as reclamation works. And these are the technologies that I'll be sharing shortly. It covers a mixture of both of these works. So in summary, we've categorized our digitalization strategy into these broad aspects. And then we can further break them down into the individual use cases as well, which we have used in several of our projects. So today, what we'll be talking about is only a few of these technologies that we have deployed that's related to smart construction. So in particular, these four are the technologies that we'll be elaborating on, starting with the unmanned K-zone installation system that we have deployed in one of our projects in Japan. So here in this corner, this is the overall construction view of a K-zone installation project. And over here, it's the zoomed in view of a single K-zone. And in this corner here, you see this big block here, it's the individual K-zone. And underwater, there will be these concrete protection blocks at the base of the K-zones for slope protection. And typically in a typical K-zone installation, there'll be several manpower standing on this K-zone during the installation and positioning of the K-zones. But what we have done here is to replace the manpower with sensors, cameras, GPS and whatnot on the K-zone, so that we can remove the manpower required to be standing on the K-zone during the installation. So this, apart from making it less manpower intensive, it also improves safety, because these tug lines that are tied to the tugboats, these are high tension cables that there's always a risk of the cable snapping that may cause injury to workers. So all the information that's collected from these sensors are all synchronized or fed back into a centralized control center, where people on the K-zone or in the cranes and tugboats have access to this information. And it automates the pumping of the water in and out of the K-zone during the installation to maintain the stability of the K-zone. So at the same time, for these concrete block protections that's being installed underwater, typically we have divers who will help to coordinate the position of the block installation together with the crane operators. And this has been replaced with, or rather enhanced with, the divers having smartphones underwater that helps them to view what's going on above water. And it also shows them the approximate position in AR, where the installation is supposed to go. And because of the GoPro that they have with them, and also a GPS system that's mounted on the tip of the crane, the crane operators will be able to see where are the position of the divers underwater, which helps us to enhance the safety of this whole construction works as well. So the next technology that I'll be talking about is related to remote construction, about unmanned excavators. So this is not a new technology per se. So what happens here is that this crane operator is in a control room that is away from the excavator itself. This is the excavator, and you can see that there is no room for any operators to sit within the excavator. And this technology is primarily deployed in high-risk areas that are susceptible to landslides or volcanic eruptions. Another technology that's related to remote construction or assisted construction, it's a block installation support system that we are using to install these X blocks for wave protection. So this system is made up of a dedicated frame, and there are various equipment that is mounted onto the frame, like the 4D sonar, some GNSS systems. And when these blocks are lifted underwater, this is a 4D sonar image that you see, together with a 3D modeling software that was used to model the 3D blocks. The software will help to superimpose the actual 4D sonar image together with the 3D models that we have, and then predict or help the operators to identify which is the target installation position to place the X blocks. So what this does is that it helps us to reduce the time divers need to spend underwater to assist the crane operators to identify the target installation positions. Okay, so the next technology that I'll be talking about, it's related to remote monitoring. And this is one interesting technology that we have implemented or developed in Japan. We call it the iBoat. So this is the boat that you see. And on the boat, it is mounted with several sensors, cameras that enables us to take photos and videos. And because of the small size of the boat, it can easily access spaces like this underneath piers to check the structural degradation of the structures. So this is the photos that the boat takes, and we can translate the photos and videos into a 3D model that you see here. So from this 3D model, the images and videos are fed into a software that can do automatic identification of crack width analysis. So then based on this crack widths that it identifies, it automatically determines the deterioration level of each of these structures and gives a sample report like that you see here that is colored. So this helps assets or building assets or civil infrastructure assets people understand what is the current structure degradation of their structures. So this video here, it's a boat in operation. This is the boat that is moving, remote controlled by somebody who's standing on the pier. And this is the video that the controllers are seeing. And you can clearly see how badly the structures are degraded. So apart from that, because all of this information is digitized, we can capture the information in a timeline, and then eventually we can compare how long it takes for the structure to degrade and so on. So of course, because of the remote control capabilities and the small size of the boat, we can improve the efficiency of the inspections by about half. For a traditional inspection, we can cover about 1,002 meters square per day, but the boat can cover approximately 3,000 meters square a day of inspection. And the last technology that I'll be covering, it's how we use AR/MR, which stands for augmented reality and mixed reality, for geotechnical visualization. So this technology is more software-based, where we call it the iPenta-Call, which stands for the Penta-Ocean Construction Information Collection and Sharing System. So what you see here in this view here, it's an integrated system where we can collect all the various data from design data, like the geological profile, the drilling data, as well as site information like the tunnel face photographs that we obtain as we mine through the tunnels. Also design information like the borehole data, information from BIM that you see here, that contains the tunnel supports, or data from the instrumentation and monitoring equipments that we obtain, such as the ground surface displacement data. So the overall system setup overview looks something like that. We have the various equipments that are mounted on site to collect the information. There's like tunnel face photographs that the engineers obtain as they mine through the tunnels, or any observations or additional comments that engineers need to make as they are doing their field inspections. So since all of this data, it's all contained in the cloud system, people from the client's office, they can access this information anytime to view the data that they want to view, or people from our field office or branch offices, they can also see all these models in 3D in a VR environment and communicate with people in the field office who are using MR headsets to see what they are seeing. So people from the branch offices can actually view through the field officers engineers headsets of a superimposed model of the virtual models together with the real environment where the site engineers are looking at. So this helps to improve the communication between the branch officers and the field officers for information transfer. And the last software technology that I will be talking about, it's what we call the GISIM, which stands for Ground Improvement Construction Information Modeling. So this is quite similar to a geotechnical visualization software. And in this video, what you see here, it's a combined model of BIM as well as the information from the GISIM software. So the GISIM software is able to extract data from Excel and automatically create this grout injection tube locations and create it into a 3D model, which we can put it together with BIM to identify clashes that we might occur with existing utilities and such. So this kind of technology, it will help us to improve our construction productivity and also like reduce any potential risk during our construction. So next, I will hand it over to my colleague Edward to explain to you more about how we use our databases to create like detailed geotechnical models for this kind of analysis.
Good morning, ladies and gentlemen. Going forward in this presentation, Penta-Ocean uses Leapfrog Works to import 3D structural models from BIM to model the unique and variable geological characteristics for our projects, to convert geological borehole data into the 3D models we use, to provide a realistic guidance that we can use to minimize risk and for collaborative decision-making. To enhance the geological understanding as data files are added to the project, and to predict any selected point of the project underground, what the geological condition is expected to be. Next is a demonstration of modeling the rock head and soil profile. To model the rock head in relation to the planned tunnels and shafts from the borehole logs, we import the borehole data. We start with a select group of boreholes. The geological data from the boreholes is categorically separated into rock, soil, mix, clang, or fill. The rock contact layer is drawn, as you see here, and it's overlain by the mixed zone. In the orange, and then by the soil zone, the green. Then the clang formation extents are added, overlain by the fill layer. Then the shafts and tunnels are brought into the 3D model. And now we can see from any vantage point where that rock head will occur in the tunnels and the shafts. Similarly, this is a demonstration of the modeling the project weathering profile from the borehole data. First, we show only the S2 intercepts And then we've just added the S3 intercepts. The red are the S4, the pink are the S5, and the light pink are the S6 profiles. Now we turn on the S2 solid, the S3 solid, the S4 solid, the S5, and the S6, and then add the tunnel and shaft locations. We look down, we can make a slice section and rotate that section. And now we can see using transparency into the project, and we can move those slices to any location we want to have a better idea of what the conditions will be. Now we are making a longitudinal section, once again rotating. And here we've combined the geological model with the tunnels and shafts. And so we've actually said, what do we think the conditions will be as we excavate the tunnels and shafts at what location? This is combined weathering, and it's great for visualization and planning. So here the shaft and tunnel excavations have been modeled and made a slide. We've computed the excavation volumes and the weathering grade. This shaft in the lower left-hand corner, for example, will produce 15,506 in situ cubic meters of S3 grade. Any color represents a weathering grade, and we can estimate the volume by clicking on that location, and it will show us the volume. Excavation volumes are useful to know and plan for in advance for the tunnels and shafts, because differing grades of material have to be dumped at differing locations. And each location has a difference in transportation costs and dumping costs. So knowing this in advance is a great help for planning. Now we're going to look at TBM rings, which we plan and model into the Leapfrog models. Every ring has a planned location with an XYZ coordinate and a number. So we can plot these into the model. Then rock characteristics are cataloged as the TBM excavates that particular ring. Tunnel face records can be used to model geology because they're close spaced in relation to wide spaced boreholes. Incorporating ring locations into the model provides a real-time understanding of the TBM cutter head location and the rock characteristics found at that location. By knowing the location for each ring, a prediction about the rock type, weathering, permeability, rock strength, abrasivity can be made and compared to the actual ground conditions. This is called ground truth. These comparisons are valuable functions for planned and unplanned cutter head intervention locations, because some interventions, as you know, can take days to complete. Project schedules can be improved when cutter head intervention locations can be planned to the optimal locations. This next slide is a video that we take of boring machine rock cuttings passing over a separation screen headed for the slurry treatment plant. We take these at every ring, and this video specific ring number is cataloged into our database for future reference. And here's a photo of the fine and rock material grab samples collected at the same ring number. Again, these are cataloged and kept in our database. This next video shows how faults and fracture density, or RQD, from borehole data can be modeled. When televiewer data is available, we can model faults, bedding, and joint orientations. We start here with a plan view for numeric modeling of fracture density, or RQD. The red is poor, the pink is very poor, the green is fair to good. So we focus on the pink and the red areas. We know the rock is highly fractured. So this helps to identify suspected fault zones. Now we can put in additional boreholes using a televiewer survey. And if we find, we can identify the strike and the dip of these fault zones. So there we make a longitudinal section, which we can rotate. We can project the fault zones outward from the boreholes, which helps us to anticipate ground stability and support requirements. Some additional things we're doing with Leapfrog Works for geological modeling: soil penetration, SPT tests, total core recovery, solid core recovery, rock strength, permeability, rock abrasivity, plasticity, ground improvement and ground injection, locations and quantities, and virtually any data that can be numeric or categoric can be modeled, and most of this data can be modeled in combination. Some of the construction technologies that Penta-Ocean has used in our projects to improve productivity and quality are unmanned and remote construction, remote monitoring and image analytics, uses of augmented reality and mixed reality for remote collaboration, and better visual understanding. So this ends our presentation today. Thank you very much. It's been a pleasure. Have a good day.
Thank you, Michelle and Edward, for sharing a very insightful presentation with us. So moving on to our next speaker, may we invite Mr. Michael O'Connor, General Manager, Head of IDD Gammon Private Limited, to present his presentation topic on Sentosa Sensory Scape, digitally stimulating the senses. Over to you, Michael.
Good morning to all the webinar attendees this morning, and thank you to SCAL for inviting me to share about our project on Sentosa. So let me just open up my slides. Okay, I'll just pause for a moment. I think what I'm trying to do today in the presentation is to show you some real use case examples of some of the digital technologies that we deploy at Gammon. This cover page is a view of the project that we're doing. It's a very unique, bespoke project with some extremely challenging structures. You can see these three two-way curve vessels, which are the key attraction points on this new development, two steel vessels and a precast concrete vessel. Later on in the presentation, I'll share with you some of the challenges of those to develop from a conceptual model into a fabrication model and prefabricated components. This slide is Gammon. Gammon, for the last 2 years, we've been slowly building up our capabilities on digital technologies. We've now developed an integrated digital platform. At the core of that, obviously, is a common data environment, the CDE, and all the other technologies that you can see along the perimeter actually will input the data into that single source of truth, that CDE. So this is our corporate template in terms of different technologies. we develop our own apps in-house as well, which I think I'll share with you later on in the presentation. But all of these will feed into this central data management information module. So really, it's the sum of its parts that work on our project. So finding the right tools for the job. I think we got to ask ourselves, what does the client want? And what digital tools do we prescribe for that project that will resolve the challenges and issues? We have to understand the deliverables first before we design the digital tools. I think for Gammon, I think when we implement any digital initiatives or innovations on our project, we have to have a real value that comes out of the back of it that we can demonstrate. Otherwise, it becomes digital bling that you're putting on your project with no real benefits to the company. So again, building an IDD ecosystem, defining our toolbox. This is the starting point of the project. So again, we defined what our CDE would be and what our collaboration platform will be for the design, coordination, and development. Those sit at the core, the heart of the IDD ecosystem. LiveBIM and Revisto, which we'll show later in the next slide, are the key technologies in terms of information exchange and data integration. On the perimeter, you'll see we've got a number of different softwares which are actually implemented to do different tasks. We've got 3D laser scanning, drone photogrammetry. We've got the VR immersive space, CCTV, computer vision, which is AI running off the backbone of the CCTV cameras. A number of initiatives and technologies, but all of these were selected to do a certain task and to actually give us some value on the project. So at the bottom, you can see again, as I mentioned, in terms of cloud-based solution for project information and BIM collaboration, we have the CDE, which is key. That's where all your project information and documentation goes in. And there's a number of different CDEs on the market. We selected this one for this project. This one will integrate the prefabricated components, and those will come back into the CTE and will update the BIM model to show which components have been installed. I think at the bottom, you can see the Revisto. As I said, it's a very complex project. There's a lot of interfaces. It's a one of its kind with different geometries meeting together. So as a collaboration tool for all the stakeholders, the contractors, the client, the consultants, to have visibility of the design as it develops is extremely valuable. Parametric modeling. We decided at the beginning of this project, I think with the complex two-way curve geometries that were involved in these vessels, we needed some assistance with a software. So we selected Rhino. The benefit of Rhino is you can automate multiple diagrid variants when generating the form of the vessel. And it saves its productivity savings in terms of BIM resource time, an automated number of different options that you can present to the client and the consultant to get it resolved. So this is a capability we developed in-house, and we were careful to select our subcontractors and vendors that had similar in-house capabilities. The importance of that I will share with you later. So this is actually what you can see on the screen. This is for the precast, one of the precast vessels. We actually had to do, even the rebar was modeled parametrically to conform within the volumes of the precast shapes. Very, very complex. You can see on those, and it's, without Rhino, I think would have been unable to develop. And of course, your fabrication drawings that come out of the back. So this is the Gardner Smell. It's one of the steel vessels. Again, 75% of this project has been prefabricated. So the importance of developing a workflow from the design model through to the construction model, and in the end, eventually to the fabrication model was key. So for this, we had Rhino, which we export an IFC file into Tekla. DWG comes out of Tekla. It goes into AutoCAD 3D. And from there, finally, we bring the IFC file from there back into our Revit, which is our master model file. So again, the workflows are very key. The software's interoperability and open BIM concept was key that we could maintain this seamless workflow. Again, this is the Garden of Sound, which is the other steel vessel. Essentially water bowls running up the whole length of the vessel with cascading water down, which generates the sound. So another one of the Sensory vessels also worked together with our steel specialist who developed the fabrication drawings in Tekla, and then those were exported out into the drawings for fabrication in the factory. So again, very important to find the right supply chain partners and vendors that have those in-house capabilities. And the final vessel we share, this one is the precast vessel, probably the most challenging of all. Certainly in terms of the connections and the joint details that went into developing this vessel. These vessels are about 13 meters high by 23 meters wide. So they're very, very challenging structures. And I think without these, without the technologies or the softwares that we used, I don't think we'd have been able to deliver a project like this. So it's digital transfer of files all the way through the chain, from the consultant to the contractor to the specialist vendor to the factory fabricator and back to the main contractor to put in for our as-built model. We've looked at doing using Cubicost for 5D cost-driven applications on the project. We're looking at using this to help procure major packages. So again, the model file will go into Cubicost software. We're able to model automatically model the rebar inside the RC structure and get the quantities out. And we've been using this software tool to help the site procure major packages. And that could be tile finishes, that can be architectural metalwork, but it's definitely facilitated and given us very robust quantities during the course of the project. Okay, I think it was mentioned earlier in the introduction about the use of drones on site. Now, obviously, it's a linear project. It's about 400 meters in length. We deployed drones from the very beginning. There's about 6 to 7 meters of levels that we needed to excavate down to get to the foundation base for the new structures to come in. So we've utilized this drone footage, which generates 3D mesh maps for site utilization and also for progress monitoring. It's a very useful tool. It goes onto a cloud-based platform, which the client, the stakeholders have visibility on a weekly basis. Just to add, this is an in-house capability. We've sent 6 of our staff for drone licenses so we can operate independently on our own on our project sites. This is a view of the output that you get. Obviously, the platform here stitches together thousands of photos taken during the flight. It can generate this as a cloud point model for you or a textured mesh model. What are the benefits of this? Well, I mean, you can go into this model. It's within 20 to 40 millimeters tolerance of what's actually on site. You don't have the same level of detail you get with laser scanning, but it's very informative in terms of planning your site, utilization, plant and equipment, where you can come in. And I think I'll also show you another use case for this, for this information when we export it out, how we can use it to facilitate progress monitoring, real-time progress monitoring. So the key is stakeholder visibility, and we can also use this data to support our progress claims with the client. Okay, this is looking at combining reality capture with 4D BIM. This is Fuser VDC. We've integrated the Primavera program into Fuser. We've linked all the task bars with the BIM components. So obviously, as you slide along the program date, you will see what is your target program, how much you're supposed to construct at that point in time. But now what we've looked at is actually integrating the textured mesh model that we've got from the drone flight. We're able to incorporate this into the overall model, and we're able to see on that date, that target date where we're supposed to be, say, casting our footing or our slab to the vessels, whether we've excavated down to the correct level or not. So this is going to be a very powerful tool for us moving forward in terms of monitoring the site readiness for the next task to come in, or in terms of actual progress as well. So this is something we've not used before, but I think we're all getting quite excited about being able to do this integration. Now, with 75% of DFMA on this project, that's an awful lot of prefabricated components that are going to be done off-site. It's going to be key because the steel is being prefabricated in Malaysia. The precast components are being cast in China. So there's a real risk for us in terms of certainty of those prefabricated components. How do they fit? How will they be assembled together when they come to Singapore? How do we check the quality control? How do we validate the geometry of these prefabricated components? So we're implementing 3D laser scanning technology. The laser scanning will be done in the factory. The data will be sent to us. We will process that cloud point data, and we will bring it into the BIM model to check on the alignment, the tolerance, and geometry of each of these prefabricated components. Only when we're satisfied that this meet the criteria and the tolerances inside the model will we release the prefabricated components from the factory for delivery. So this is, it's actually a technology that replaces the use of manpower going to visit the factory and to validate that the components are ready to be shipped. Another example, these are the precast, 3 precast segments that have been assembled in a factory. Again, we need to check that this, how is this in terms of the fabrication model, the BIM model that was developed? Have they been cast once the formwork is out? Will they conform to the 3D geometry when these were assembled? So I've shown you this. This is basically what is generated. This is the data we get, the cloud point data from the scan. Obviously, there's a lot of things inside the scan that we don't need. So you first go through the process, cleaning up the cloud point information that's not required. So essentially just cutting in and around your precast component, cleaning it up so that it's ready to then import into your model. So you see this one is just tidying up, clearing out everything that's not related to the precast model. And then you bring it into the Revit file and you check the alignment of that precast component to make sure it's conforming to the shape. This gives you certainty, I think, when the prefabricated unit is sent, you've got confidence that they're all in the right geometry and there should be no issues during installation. Immersive BIM, the VR immersive environment. We've used it in a number of ways on Sentosa. I think this is, and certainly during the COVID restrictions and trying to recreate the bubbles between head office and site teams to keep them segregated. We've been able to use a BIM matrix software that allows multiple users from multiple locations to be inside the same space in the same model at the same time, collaborate, comment, do markups virtually. And this is something that's actually helped us during the CB period where we weren't able to visit site, where there were shutdowns. So very good use of this technology. I think the other way, I think getting a return, obviously, some people may ask in terms of the investment that goes into bringing these technologies to our project, to our site. I think we're already starting to see some return on that investment. We're doing virtual mock-ups and inspections of the design. So they're rendered photorealistic. We've got the actual paint colors applied. This is the steel vessel you're looking at. Originally in the contract, we had 2 different tones on the steel vessel, but by bringing the architect into this immersive space, walking around his project, seeing it with a single tone color, we were able to convince him to make the design change, which obviously saved us a lot of time in terms of the protection would have had to do to that vessel on site. So these are some of the benefits, tangible benefits that start coming back out for the company. Sensors, just a very quick one. We are using sensor technology. The precast vessel, if you see in the middle there, will be casting into the joints a sensor, a GeoDNA sensor that will actually transmit data on any tilt or movement within that precast structure as it's constructed and assembled. The good thing about this is actually for 3 to 4 years after the completion of the project, we'll continue to get data from those sensors, which will inform us whether there's any movement in that structure after completion or during. I mentioned earlier computer vision. Gammon have got their own app developed, which is riding off the back of the CCTV cameras. We've got 13 cameras on site. We're able to track our workers. We're able to monitor our plant and equipment, restricted zone for safety management, and even down to using the AI algorithms to detect whether workers are wearing their PPE. And maybe even extend it to doing safe distancing between workers. I think the other thing is we invest a lot of time and resources in developing the BIM model. So how can we use it to improve our safety? Some of these are examples of we do pictorial method statements to help our site operatives understand the complications or the eccentricities of some of the installations and work it out pictorially. So we've got a very clear, viable sort of method statement that can be shared with all our site team and with the client and consultant as well. And finally, the smart entry and data transfer back to HR. Obviously, with COVID and the new safe management measures and they've been rolled out for entry, controlling healthy workers onto the site. We've got the thermal facial recognition cameras, but in itself, that's not a great technology. I think they're being deployed everywhere now in Singapore. But with some API integration into our HR system, we're able to get that data transmitted directly back to the HQ for payroll. So it's that integration part that is actually, again, helping us in cutting out the middleman. And last slide is the putting our technology in the hands of our operators. So making sure that they can take out their mobile phones, their tablets out on the site, so the BIM model can be brought out to site to make use of it. Our applications can be basically the objective is to keep our operatives on site to manage the works and try and keep them out of the site office. And that's it. Thank you.
Great. Thank you, Michael. So ladies and gentlemen, we would like to proceed with the Q&A session, and may I invite Michelle and Edward to join us. Right, so we will start with the first question. Any sensor real-time monitoring of stress ground movement at tunnel face or shaft during boring to ensure safety? I suppose this is for Penta-Ocean.
Can you repeat the question one more time, please?
Right, any sensor real-time monitoring of stress ground movement at tunnel face, shaft during boring to ensure safety?
Well, boring is usually done before the shafts are installed. However, if there's boring activity after, and I'm expecting you're talking about tunnel boring, the truth is we have many sensors inside the shafts. We have tilt meters, we have motion meters, we have convergence monitoring, as well as a number of boreholes around the site with piezometers. So very intense monitoring takes place around the tunnel boring machine as the machine advances. And that relates to the shafts and surrounding structures, including buildings above ground, settlement markers, ground settlement, compression in the Kalang Formation. So the short answer is yes. Very intense monitoring takes place.
Okay, so we have another question. This is for Michael. How does Gammon ensure the subcon plug into your digital platform?
Okay, I think I mentioned at the beginning. I think actually for a digitally run project, with the amount of initiatives we put in place, we actually factor that into our selection of our subcontractors and our vendors. So, for example, the steel specialist subcontractor, we knew that they had in-house capabilities for Tekla modeling, for doing the fabrication drawings. So that was one of the key decisions. It's not necessarily the cheapest contractor we'll go to, but we'll look at their in-house capabilities so that they can plug in to our digital platform, essentially. So I think that's the key, selecting the right subcontractor that can plug into our platform.
Okay, we have a question for Michelle. Can you share which projects had implemented the unmanned caisson installation? We can't hear you, Michelle. Sorry, Michelle, we still can't hear your voice.
Oh, hello, can you hear me?
Yes, now we can hear you clearly.
Yeah, so we use this system in the construction of South Offshore Breakwater at Hososhima Port in the Kyushu region of Japan.
So in interest of time, I think we will take one more questions. How sensitive are the sensors? What are the tolerances, i.e. plus minus in centimeters? This question goes to Michael.
It's actually in millimeters. So I think in terms of obviously for the precast vessel, at every single joint, we need that tolerance to be in millimeters in terms of any settlement of the structure as it goes up. So it'll measure down to below a millimeter. It's very sensitive, these sensors.
Okay, so in interest of time, so sorry, we can't take all the questions. We can't respond to all of you. So once again, thank you, our three speakers, Michael, Michelle, and Edward.